topic Ionic equilibria starts with the concept of conjugate bases and conjugate acids. So firstly, what are acids? Acids are substances that donate an H plus ion in their aqueous solution. Acids are of two types: strong acids and weak acids. Okay. Now, acids, whenever acids dissociate, they give a conjugate base, right? So let's see how it goes. So strong acids ionize fully, and they give a weak conjugate base which cannot accept protons easily. So an example of a strong acid is HCl. When it dissociates, it gives an H plus ion and a chloride ion. So when an acid dissociates, it gives an H plus ion and a conjugate base over here, that is Cl negative. Now because this is a weak conjugate base, it cannot accept a proton easily. So that's why the reaction is not non-reversible. Whereas in weak acid, it ionizes partially and it gives a strong conjugate base which can accept a proton easily. So an example is ethanoic acid. Ethanoic acid dissociates into H plus ion and the conjugate base which is ethanoate ion. Ethanoate ion is a strong conjugate base, so it can accept a hydrogen ion easily, which is why this is a reversible reaction. Now next is bases. So bases give a conjugate acid. Acids give a conjugate base, bases give a conjugate acid. Now again, there are two types of bases, strong and weak. Strong bases ionize fully and they give a weak conjugate acid which cannot donate protons easily. So the base sodium hydroxide dissociates to form sodium ion and hydroxide ion. The sodium ion is the conjugate acid, but because it's weak, it cannot react with OH negative. It cannot donate a proton to OH negative, which is why this is not reversible. A weak base ionizes partially and gives a strong conjugate acid which can donate a proton easily. So that's why, so for example, there is ammonium hydroxide. It dissociates to form the conjugate acid NH4 plus and hydroxide ion. The NH4 plus ion can donate protons easily because it's a strong conjugate base. It can react with OH negative to form NH4OH again, which is why this is a reversible reaction. And NH4OH is usually written as ammonia aqueous. There are some examples of reactions of acid bases and acids. So in the first reaction, there is water plus hydrogen iodide forming hydronium ion plus iodide ion. So over here, the water is accepting hydrogen, so that's why it's a base, whereas hydrogen iodide is donating, so it's an acid. So H2O is forming H3O positive, which means that H3O positive is a conjugate acid, and HI is forming I negative, so this is a conjugate base. Then there is water plus ammonia producing ammonium ion plus hydroxide ion. So over here, water is donating hydrogen, so it's an acid. Ammonia is accepting hydrogen, it's a base. Ammonium ion is a conjugate acid because it's formed from ammonia, which is a base, and hydroxide is a conjugate base. Now this is general reaction of CH3OH plus HZ forming CH3OH2 plus Z negative. So Hz is donating an electron, is donating a proton, so it's an acid. Z negative will be a conjugate base. CH3OH is accepting a proton, so it will be a base, and this will be a conjugate acid. Over here, CH3NH2 plus HCl, CH3NH3 plus Cl negative. HCl is donating a hydrogen, so it's an acid. Cl negative is the conjugate base. CH3NH2 is accepting hydrogen, so it's a base. This is a conjugate acid. So that's basically what a conjugate acid and a conjugate base are. This topic is ionic product of water, or the water dissociation constant. So basically, water dissociates into hydrogen ions and hydroxide ions. However, the dissociation or the ionization of water is very low, which is why the concentration of water is approximately constant. Very few ions are formed, so most of water remains in liquid form, right, which is on the left side of the equation. So if we wanted to find Kc, which is the concentration of product upon reactants, so that would be H plus in concentration of hydrogen ions, hydroxide ions, and the concentration of water we've taken as constant. So we get this. Now Kc into K is written as Kw, which is called the ionic product of water or the water dissociation constant, right? At 25 degrees Celsius or 298 Kelvin, the water dissociation constant has a constant value that is 1 times 10 power negative 14. And as you can see, this is a very small value, which shows that the ionization of water is very low. Basically, this value shows the concentration of the products formed, and because it's the product of it's the multiplication of the products basically. So this is a very small value showing that very few products are formed. So water ionizes very less. Now, if you want to use this to find a concentration of hydrogen ions at 25 degrees Celsius and 298 Kelvin, so how do we do that? So basically, we know that from this equation, the molar ratio of hydrogen ions to hydroxide ions is 1:1. Therefore, the concentration of hydrogen ions is equals to the concentration of hydroxide ions, right? So in this equation, I can write it like this, right? So I know the value of Kw at standard conditions. This is equals to H plus squared. So hydrogen ion concentration will be equals to the root of times 10 power negative 14. Therefore, hydrogen ion concentration in standard conditions is 1.0 times 10 power negative 7. Right? Now, one more thing. This was the value of Kw. Now, if you want to find the value of pKw, that is basically negative log base 10 with multiple Kw. So P, wherever P comes in the chapter of Ionic Equilibria, it will represent negative log base 10. So in the calculator, this is basically this symbol. So you press this symbol and then you just input the value of Kw. Over here it will be 1 times 10 power negative 14. You'll get a value of 14. So pKw for at standard conditions is it will be negative log, right? So that will be 14. Is the relationship between pH and pOH. So pH, as we all know, is basically a measure of the concentration of hydrogen ions in a solution, right? So to find the value of pH, the equation is pH equals to, again over here we have P with H, so P represents negative log base 10 and H is the concentration of hydrogen ions, so it's negative log base 10 concentration of hydrogen ions. pOH represents basically the concentration of OH negative ions. For this, the equation is pOH is equals to negative log concentration of hydroxide ions. However, this is not in syllabus because most teachers teach it just to clear some concepts, so that's why I've mentioned it. This relationship again is not in syllabus, but it helps in understanding. So basically, we know that Kw, the water dissociation constant, is equals to hydrogen ions concentration into hydroxide ion concentration. If we take negative log on both sides, so negative log Kw is equals to negative log H plus. Again, this derivation is only for math students. For non-math students, you can just directly learn this result. So basically, from this, we can get negative log Kw is pKw. You can write this as negative LgH plus minus LgOH negative. Math students will know the properties of logarithms. Then Kw we know for water at standard conditions is 1.0 times 10 power negative 14, right? And then negative LgH plus is pH, negative LgOH negative is pOH. So pH plus pOH, the value of this is 14. So pH plus pOH is equals to 14. Again, not in syllabus, but it's just for the understanding. Calculations related to strong acids and strong bases. So the first question is calculate the pH of 0.01 molar HCl. So HCl we know dissociates into H plus Cl negative ions, and it fully dissociates as it is a strong acid. So if the concentration of HCl was 0.01 molar, So H plus will also be 0.01 molar, right? So that means that the concentration of H plus is 0.01 mole per dm cube. So pH is equals to negative log H plus concentration is equals to negative log 0.01. So that is negative log 0.01. This is equal to 2. So pH is equals to 2. That is the first question. Calculate the pH of 0.1 molar H2SO4. These are very basic questions. H2SO4 dissociates into 2H plus SO4 2 negative. If the concentration of H2SO4 is 0.1 molar, concentration of H plus will be half of that because the ratio is, twice of that because the ratio is 1:2. This will be 0.2. So pH is equals to negative log 0.2. So pH is equals to 0.6989, that's approximately 0.7. Next question, calculate the pH of 0.01 molar NaOH. Right. So over here, one thing we could have used was the concept of POH. However, because it's not in syllabus, so we will try not to use that. So we'll be using the water dissociation constant, which is equals to H plus and OH, concentration of H plus times concentration of OH negative. Right, now NaOH dissociates into Na plus OH negative if there is 0.01 molar NaOH. So OH negative will also be 0.01 molar because it's 1:1 in the ratio. So Kw we know is 1.0 times 10 power negative 14. H plus ions we have to find. OH negative we know is 0.01. So through this we can find the concentration of H plus ions. This is negative 14, sorry. So 1 times 10 power negative 14 upon 0.01. 1 times 10 power negative 12 mole per dm cube. So pH is equals to negative Lg 1 times 10 power negative 12. pH is equals to 12. Next question, the pH of H2SO4 is 1.8. Calculate OH negative, the concentration of OH negative ions in the solution. Right, so pH is equals to negative log H plus concentration. pH is 1.8 equals to negative Lg H plus. I can write this as 1.8 equals Lg H plus. Now math students will know this, but for non-math students, when we have to solve logarithms, so basically what we do is that if it's log base 10, that's Lg. So basically you write this as 10 power negative 1.8 equals H plus. Right, so just learn this method. To remove the log, take the other side to the power 10. Make the other side the power of 10, right? So through this you'll get the concentration of H plus ions, which will be 10 power negative. Let's just leave it over there. Yeah. So now they're saying calculate the OH negative ion, concentration of OH negative ions. So Kw is equals to H plus OH negative 1 times 10 power negative 14 equals to 10 power negative 1.8 times OH negative concentration. So OH negative concentration will be 10 power negative 14 upon 10 power negative 1.8. 6.3 times 10 power negative 13 mole per dm cube. Then the pH of NaOH is 12.9. Calculate the concentration of H plus ions in the solution. This is pretty simple. 12.9 is equals to negative Lg H plus. So negative 12.9 equals to H plus concentration. So H plus concentration is equals to 10 power negative 12.9. So basically 10 power negative 12.9 is equals to 1.26 times 10 power negative 13 mole per dm cube. In the next question, 4.6 gram of NaOH is dissolved in 100 cm cube of water. Calculate the pH of NaOH. So 4.6 gram of NaOH is dissolved in 100 cm cube of water. So I'll find the moles of NaOH. 4.6 upon sodium is 23 plus 16 plus 1, it's 40. So the number of moles are coming 0.115 moles. Now to find the concentration of NaOH, basically we know that N is equals to C into V upon 1000. So we have 0.115 equals to C into the volume is 100 upon 1000. So through this we get concentration as 1.15. This is the concentration of NaOH. So in NaOH we know that the dissociation is Na plus plus OH negative. So the and the ratio is 1:1. So the concentration of OH negative ions will be 1.15 mole per dm cube. Now using the Kw expression, so Kw 1 times 10 power negative 14 is equals to H plus concentration times OH negative concentration, which is 1.15. So H plus concentration is coming equals to 10 power negative 14 upon 1.15. This is 8.69 times 10 power negative 15. Right, so we got hydrogen ion concentration. Now we have to find pH, which is equals to negative log hydrogen ion concentration, negative Lg 8.69 times 10 power negative 15. So negative log is coming equals to 14.06. So pH equals to 14.06. Now the next question is the pH of NaOH is 12.8. Calculate the concentration of NaOH in gram per dm cube. Okay, so 12.8 is equals to the pH, that is negative Lg H plus concentration. So H plus concentration will be, log of H plus concentration will be negative 12.8. H plus concentration will be 10 power negative 12.8. Right, this was the first step. Now after that we'll use KWL expression. So Kw equals to H plus OH negative. This is 1 times 10 power negative 14. H plus concentration we have, that is 10 power negative 12.8, and we have to find the OH negative concentration. Right, so that will be 10 power negative 14 upon 10 power negative 12.8. This is 0.063 mole per dm cube. Now from the equation we know that NaOH Na plus plus OH negative, so the molar ratio of NaOH and OH is 1:1. So the concentration of NaOH is also equals to 0.063 mole per dm cube, but we have to convert this to gram per dm cube, right? So to convert moles into mass, basically we know that moles is equals to mass upon mR. So over here we have moles, we have to convert that into grams. So converting moles to mass, we multiply it with the mR. So we'll multiply 0.063 times 40, gives us 2.0 2.52. We can round it off to 2.5 grams. So this is gram per dm cube, sorry. So this is the concentration in gram per dm cube. Okay, so I'll go over these type of questions once again quickly. So basically, I'll just show the questions from the first one. So basically, if you have to find pH, then your aim has to be to somehow find the hydrogen ion concentration, because then you can apply this formula and find pH, right? So over here it's pretty basic. You have the concentration of hydrogen ions through the simple equation, right? But however, if you have the concentration of an alkali and you have to find the pH, right? In that case, what you'll have to do is you'll use the Kw expression. You have the concentration of OH negative and Kw, you'll find H plus, and then use this equation again to find pH. So that's two types of questions. After that, this is now when we have to find the concentration from given pH. So over here we had the pH given, so we use basically we have pH is equal to negative Lg H plus. If you have hydrogen ion concentration, you can use this method to find if you have the pH, you can use this method to find the hydrogen ion concentration. And then because we have to find hydroxide ion concentration, so we'll use the Kw expression and find hydroxide ion concentration. Now over here there was this is simple, I guess. Then in this question we had the mass of NaOH and its volume, and we have to find the pH. Again, we have to find the pH, so we have to aim for the hydrogen ion concentration. So for that, because we have an alkali over here, so first we'll have to find the hydroxide ion concentration, then use the Kw expression to find the hydrogen ion concentration. So to find the hydroxide ion concentration, I found the moles of NaOH and then the concentration of NaOH. Then through this equation, I found the concentration of hydroxide ions. Through the Kw expression, I found the concentration of hydrogen ions, and through the pH expression, I found the pH of the solution. In the last question, there was pH given of an alkali, and we have to find the concentration. Again, it's pretty simple. You find the hydrogen ion concentration using this method, then you find the hydroxide ion concentration using the Kw expression, and once you have the hydroxide ion concentration, that is the same as the concentration of NaOH because the ratio is 1:1, and then you just convert it to gram per dm cube. I hope it's clear to you. Now the calculations that we did were for a strong acid or a strong alkali. Now the third type, which is in our syllabus, is a weak acid. So for weak acid, we use the acid dissociation constant, which is represented by Ka. So firstly, if this was an acid, it reacts with water, it would produce a hydronium ion plus a salt, right? And if we remove water, then we can simply write this as the dissociation of the acid as H plus and A negative, right? Kc for this equation would be H3O positive concentration into A negative concentration upon Ha concentration into H2O concentration. Now water, again, as I mentioned earlier, dissociates, ionizes very slightly, which is why its concentration is constant. So I can take that as K. So I shifted K over here. Now Kc into K is basically equal to Ka. And over here we had H3O positive, but as you know that H3O positive is H2O plus H plus, right? So the concentration of H plus is equal to the concentration of H3O positive. That's why I replaced H3O positive with H plus. So through this we got the expression for Ka, which is equals to the hydrogen ion concentration into the concentration of the salt upon the concentration of the acid. And the units of this depend on the equation. The units in case of monobasic acid, as we took over here, monoprotic acid, right, that are mole per dm cube, because H plus, this is the concentration into concentration, so that's mole per dm cube times mole per dm cube upon concentration, so mole per dm cube. So these two get cancelled, so the units are mole per dm cube. However, if there was like a 2 over here, so that would have come as a whole, as a square over here. In that case, there would be no units. So you have to see that depending on the equation, as we used to do in KC and KP and AS. So once this is done, then we know that P represents negative log. So pKa represents is equals to negative log of Ka. Now one more thing to state is that if value of Ka is high, then because of the negative log, the value of pKa is low. And what this represents is basically Ka being high represents that the concentration of products is more than the concentration of reactants, which means that equilibrium is lying towards the right hand side. This means that the acid is strong and it dissociates more. So the higher the value of Ka or the lower the value of pKa, the stronger the acid, and then vice versa. So after that, now this is an acid and its dissociation, and over here, because it's a monoprotic acid, so we know that the concentration of hydrogen ions will be equal to the concentration of the salt. This is the salt, so there's a 1:1 ratio, so they're equal, right? So in the expression that we read on the previous page, in this expression I can replace this salt's concentration by the concentration of H plus ions, right? So that gives me H plus ions concentration squared upon concentration of the acid is equals to Ka. I shift concentration of acid towards the left, I get this expression, shift the square, make it a root, then take negative log on both sides. Negative log of H plus is basically pH, negative log of Ka into root of Ka into acid concentration will be written as it is. So this is the expression for pH in weak acids, because the acid dissociation constant, that is Ka, is only for weak acids. So we use this only for weak acids, right? Now we have a question over here. Ka of ethanoic acid is given. Calculate the pH of 0.1 molar ethanoic acid. So we'll use this equation. pH is equals to negative Lg root Ka is 1.7 times 10 power negative 5 times the concentration of the acid, that is given as 0.1. So 1.7 times 10 power negative 5 into 0.1, and so pH is equals to 2.88. Then the next question, Ka of ethanoic acid is again given. Calculate the concentration of ethanoic acid in gram per dm cube if the pH value is 2.5. So pH we know is equals to negative log root of Ka into concentration of acid. 2.5, I'll shift negative over here, so this is negative 2.5 log of root 1.7 times 10 power negative 5 times concentration of acid. So through this, to shift the log, I'll have 10 power negative 2.5 equals to root of 1.7 times 10 power negative 5 into acid concentration. Shifting the root, this will become square. So I can find the concentration of the acid in mole per dm cube. This will be equal to 10 power negative 2.5 whole squared, 1.7 times 10 power negative 5. This is 0.588. Sorry, mole per dm cube. Now to convert this to gram per dm cube, we'll have to multiply it with the MR. So 0.588 into MR of ethanoic acid. So carbon is 12 plus 3 hydrogen plus carbon is 12 plus 16 plus 16 plus 1, 60. So 60 times 0.588, 35.3. 35.3 gram per dm cube. Next question, the pKa of benzoic acid is 4.86. The pH of benzoic acid is 3.2. Calculate the concentration of benzoic acid in gram per dm cube. So we have the value of pKa and the value of pH. So pKa is equals to negative log Ka. pKa is given as 4.86 negative log Ka. So Ka is equals to 10 power negative 4.86 is equals to 1.38 times 10 power negative 5. Right, because it's a monoprotic acid, so that's why the units are mole per dm cube. Now I have the value of Ka, I have to find the concentration. So the expression for, I'll use the expression for pH. pH is equals to negative log root of Ka into acid concentration. pH is given as 3.2. 1.38 times 10 power negative 5 times acid concentration, shifting negative over there and then the log. So 10 power negative 3.2 is equals to 1.38 times 10 power negative 5 times acid concentration. So acid concentration is coming equals to 10 power minus 3.2 upon 1. This will be root. So when we shift the root on that side, it's basically squared over here, and then 1.38 times 10 power negative 5. So this is 0.0288 mole per dm cube. To convert to gram per dm cube, multiply it with the MR. The MR is given as 122 times 122, so that is 3.52 gram per dm cube. I hope it's clear. So these were the calculations for weak acid. So we've done the calculations for strong acid, strong alkali and weak acid. These are the three that are in syllabus. This salt hydrolysis. So this is used to determine the approximate pH of different salt solutions. Basically, if a salt solution will be acidic, alkaline or neutral. So first we'll take a salt that is made by a reaction of weak acid and strong alkali. So the weak acid is ethanoic acid and the strong alkali is NaOH. These produce sodium ethanoate and water. So basically over here, if we form a solution of the salt, so we need to find whether that will be acidic, alkaline or neutral. So we take CH3COO. It's a strong, it ionizes fully, it's a strong electrolyte. It forms Na plus and CH3COO negative, and then water dissociates into OH negative plus H plus reversibly. So what happens over here is that because CH3COO negative over here, if you see from this equation, CH3COOH was the weak acid and it formed CH3COO negative which reacted with Na plus. So CH3COO negative was actually a strong conjugate base because it was formed from a weak acid, whereas this sodium ion which was formed from NaOH, NaOH was a strong alkali, so sodium ion will be a weak conjugate acid. Now because CH3COO negative is a strong conjugate base, it can accept protons easily, so that's why it will react with hydrogen ions, right? And as it reacts with hydrogen ions, the concentration of hydrogen ion decreases and the equilibrium of this reaction shifts towards the right hand side. So more hydroxide ions are formed, which is why the pH increases and it is greater than 7. So that's why a salt made by a weak acid and a strong alkali will always have a pH greater than 7. Now a salt made by a weak alkali and a strong acid. So the weak alkali is NH4OH, strong acid is HCl. They form NH4Cl plus H2O. Now over here, NH4 came from a weak alkali. So it came from a weak alkali. So it's a strong conjugate base. Sorry, it's a strong conjugate acid. I've written this wrong. NH4 plus will be a strong conjugate acid, and Cl negative will be a strong weak conjugate base. So basically NH4 plus was formed from NH4OH. NH4OH is a weak alkali, so it forms a strong conjugate acid, which is NH4 plus. HCl is a strong acid, so it forms a weak conjugate base, which is Cl negative, right? Now since NH4 plus is a strong conjugate acid, it donates protons easily, which is why it can easily react with OH negative to form ammonia and water. So it forms ammonia and water. So that's why again the equilibrium shifts towards the right hand side. However, now more hydrogen ions are formed. Concentration of hydrogen ions increases, which is why the pH is less than 7. So I'll repeat this once again because I made a small mistake. So there was a reaction of a weak alkali, NH4OH, and strong acid, HCl, forming NH4Cl plus H2O. NH4OH was a weak alkali, it formed a strong conjugate acid, which is NH4 plus. HCl was a strong acid, it formed a weak conjugate base, which is Cl negative. So NH4Cl dissociated into NH4 plus and Cl negative. H2O dissociated reversibly into OH negative and H plus. NH4 plus, being a strong conjugate acid, can easily donate a proton. So it donates a proton to OH negative, forming NH3 and OH2O, which is why the equilibrium shifts towards the right hand side in this equation. So more hydrogen ions are formed, so the concentration of hydrogen ions increases and pH decreases below 7. So that's why a salt made by a weak alkali and strong acid has pH less than 7. Salt made by strong acid and strong alkali. So NaOH is a strong alkali, HCl is a strong acid, forming NaCl and H2O. A strong alkali forms a weak conjugate acid, a strong acid forms a weak conjugate base. So NaCl dissociates into Na plus and Cl negative, which are both weak conjugate acids and bases. H2O dissociates reversibly into H plus and OH negative. Now because Na plus is a weak conjugate acid, it cannot donate protons easily, so it cannot react with OH negative. Cl negative is a weak conjugate base, it cannot accept hydrogens easily, so it will not react with H plus, which is why the equilibrium stays unaffected and the pH is neutral, that is equal to 7.